In this video, I will be explaining map projections, what they are, how they work, and the math behind them. You might think that math and geography are polar opposites, but they're actually more connected than you might think. One of my favorite examples of this would have to be map projections. That's because the way we understand the world is heavily influenced by geography. Geography is dependent on maps, which themselves are dependent on math. This means that math affects how we view the world more than you might expect. Therefore, knowing the math of maps will give you a whole new level of understanding. Like a lot of things in math, this topic starts out with a single problem. That problem is as follows. As we all know, the Earth is a sphere. Paper, on the other hand, is flat. So how do you represent the entire surface of a sphere on a flat sheet of paper? The solution is you have to use a map projection. A map projection is a mathematical function that takes points on a sphere as input and produces points on a plane as output. To represent points on the output plane, we can obviously use x and y coordinates, but what about the input sphere? Well, before answering that, it should be noted that Earth is not a perfect sphere. It has elevation changes all throughout, and it's also wider than it is tall. This makes it technically an ellipsoid, but it's so close to being a sphere that for most intents and purposes, it's fine to just call it a sphere. Going back to the question though, how do we represent points on the input sphere? One technique is to use Cartesian coordinates in 3D space, but there's actually a much simpler solution. That solution is spherical coordinates, or as you might know them, longitude and latitude. Instead of using 3 distances, spherical coordinates use 1 distance and 2 angles. These are written with the Greek letters rho, theta, and phi. The distance rho represents distance from the origin. Since we're looking at a sphere though, all points on its surface are the same distance from the center, making rho effectively a constant. This means that we only need to concern ourselves with the 2 angles. The angle theta corresponds to longitude, or how far east to west you are, while phi corresponds to latitude, or how far north to south you are. They're not exactly equal though. Latitude measures angle from the equator, but phi measures angle from the top, so latitude equals 90 degrees minus phi. Also, longitude ranges from negative 180 to plus 180, but theta ranges from 0 to 360, so longitude equals theta minus 180 degrees. These distinctions determine whether 0, 0 is in the center of the map or the top left corner, and this is really important when it comes to trig functions. Also, for whatever reason, physicists switch the names of phi and theta. To avoid all that confusion, I'll just use A for longitude and B for latitude. So to determine where a point will end up on the map, based on its longitude and latitude, you just have to put it through a projection function. Each projection function is actually 2 separate functions, one for x and one for y. So if we have 2 inputs and 2 outputs, what if we just use x equals a and y equals b? Well, that results in a projection known as the Equirectangular Projection. Its formulation makes it the simplest projection there is, and many other projections are just modifications of this one. For that reason, it's sometimes called the unprojected map. It's also called plat carré, meaning flat square, referring to how longitude and latitude lines form perfect squares. Why would you want to modify it though? Well, although it does have many advantages, it also has many disadvantages. Depending on the circumstances, these can be deal breakers. To help explain these, I've created a scoring system for each map projection. There are 5 categories, and they each have scores from 0 to 4 that are added together to get a final score. But this final score isn't as important as the individual categories, so don't take it that seriously. The first category is aesthetics. This is just my personal opinion on how good the map looks. If you disagree, that's perfectly fine. In fact, finding a projection that looks good to everyone is kind of impossible. I would give flat square a 2. The second category is area preservation, or how much to scale the areas of regions are. A bad score would mean that some areas look bigger than they actually are, while a perfect score would mean that any 2 regions with equal area on the map will also have equal surface area on the globe. Keep in mind that this category doesn't care about shape. With the flat square projection, polar regions are stretched out and appear bigger than they actually are. For example, compare Iceland and Java. On the projection, Iceland looks quite a bit bigger than Java, but in reality, Java is quite a bit bigger. Flat square gets a score of 2 because it's pretty bad at area preservation, but it's by far not the worst offender, as you'll see later on. The third category is shape preservation, or how accurate shapes are to how they actually look. A bad score means that some shapes are stretched in weird ways, while a perfect score would mean that shapes are preserved on a local scale, which also means angles are preserved. This property is called the conformal property. Flat square is pretty bad at this because polar regions appear much wider than they actually are, so it gets a 1. The fourth category is orientation, or direction preservation. On flat square, no matter where you are, north is up, east is right, south is down, and west is left, giving it a perfect 4. The final category is accessibility/practicality. This represents how easy a projection is to use and understand. Flat square is probably the easiest projection to understand due to its simple formulation and perfect squares. Its easy calculations make it the standard for datasets. Also, most projections are based on it, so it has many different applications. In fact, the 3D images that I made for this video use the flat square projection to apply textures to a sphere. For those reasons, it gets a 4 in this category, bringing its total to 13. The different types of distortion that I've discussed all arise from the fact that it's impossible to unfold a sphere. That's because a sphere has positive curvature, but paper has 0 curvature. So if we can't unfold a sphere, then what can we unfold? Well, one answer is polyhedra, which are 3D objects made up of polygons attached at edges and vertices. This is where the term projection is applied literally. Imagine a candle surrounded by objects and enclosed in a room. When you light the candle, the light shines onto the walls of the room, but the objects cast shadows of darkness. Then by just looking at the shadows, you can get a sense of where the objects are, relative to the light source and each other. Now imagine those objects are continents, and you have yourself a literal map projection. As long as the walls are flat, they can be unfolded. Using a cube-shaped room results in heavy distortion. You could then use an octahedron, but even better is a truncated octahedron, which is an octahedron with the corners cut off. That results in the Waterman butterfly projection. Using an icosahedron, there's almost no distortion. Moving some pieces just a little bit results in this, the Dymaxion projection. This shows all the continents accurately, and it also shows just how close they all are. For that reason, it's often used to show human migration. Unfortunately, there's basically no sense of orientation. Sometimes east is up, but sometimes it's down and to the left. Also, the jagged edges are confusing, and they make it hard to judge distances for non-adjacent segments. The main downside of polyhedral projections is that they just don't unfold nicely. So is there anything that can go around the sphere but does unfold nicely? Actually, yes, there is. The solution is a cylinder, aka a can without the top and bottom. Even though a cylinder is curved, it has 0 curvature in the mathematical sense. That's because from a flat sheet of paper, you can curve it to create a perfect cylinder. You can't do that with a sphere though. No matter how hard you try, there's just more paper than there is room on the sphere. This is a simple demonstration of curvature. A result of this is that some things are possible in spherical geometry that aren't possible in flat, also called Euclidean geometry. For example, an equilateral right triangle. These distinctions are what make map projection so difficult, but the cylinder tries to bridge the gap. So to get from a sphere to a cylinder, we can again use projection, with a central point acting as a light source. It's impossible to cover the entire Earth this way, but you could always just make the cylinder taller. You can then unwrap the cylindrical wall to get a map. It's a common misconception that this is how the Mercator projection is made. So common in fact that I even believed it myself before researching for this video. In reality, the map you get from this is the central cylindrical projection, a map so terrible it only gets 4 points. So if this isn't the Mercator projection, then what is? Well, the central cylindrical projection is defined by x equals a and y equals tangent b. The Mercator projection, on the other hand, is defined by x equals a and y equals natural log of secant b plus tangent b. If you know calculus, you might recognize this as the integral of secant. But why is it here? Well, it's ultimately because latitude and longitude don't perfectly correspond to actual distance traveled. When you move a short distance along Earth's surface, your latitude and longitude will change by some amount. To represent these values, we will use delta A and delta B. You will also have values for actual distance moved in both the east-west direction and the north-south direction. We can call these values delta EW and delta NS. Along the Earth's surface, there are two main types of circles, meridians and parallels. Meridians are vertical and always intersect the poles. Parallels are horizontal and are always parallel to the equator. Each meridian is the same size. Parallels come in different sizes though, and this one difference is what makes map projection so difficult and interesting. When we change only latitude, we stay on the same meridian. If we change it by, let's say, 36 degrees, then we move 10% of the way around that meridian. Since all meridians are the same size, the distance moved per degree change is a constant. If we call this constant k, then we can use the variables from earlier to get delta ns over delta b equals k. This can also be rearranged. When we change only longitude, though, we stay on the same parallel. Moving 36 degrees still means moving 10% of the way around that parallel. But since each parallel is a different size, that 10% can mean different distances. For that reason, distance moved per degree change isn't constant. Instead, it depends on how big the parallel is. The central parallel, or equator, is special though. It's the only parallel that's the same size as each meridian. The rest of the parallels are smaller than it. So on the equator at least, distance moved per degree change in longitude is that same constant k from before. For any other parallel though, it's less than k. But how much less? Well, distance traveled is proportional to circumference, which is proportional to radius. In this diagram, we have a circular cross-section of the Earth. We have one parallel here and the equator here. We need to figure out how much smaller is this radius, lowercase r, compared to this radius, capital R. In other words, small r over big R equals what? To do that, we can move capital R up like this and move lowercase r down. These form a right triangle, with this angle B being the latitude of the parallel. Using some trigonometry, we can see that lowercase r over capital R equals the adjacent side over the hypotenuse, which you might remember is cosine of B. So if the radius is smaller by that amount, then the circumference is smaller by that same amount, and the distance per degree is smaller by that same amount. Therefore, distance moved per degree change in longitude equals k times cosine b. If you want, you can verify that this makes sense by plugging in values. Just like before, this equation can also be rearranged. In fact, 1 over cosine actually has its own name. It's called secant. So this equation relates distance moved east to west with change in longitude. The equation from earlier relates distance moved north to south with change in latitude. To put all of this simply, when going from actual distance traveled to longitude and latitude, there's a bias in the x direction. We then have to use these values to create a map projection. X and y represent position on the map, and delta x and delta y represent how fast those values change. Using the values as they are is what Equirectangular does. If we want to make up for the bias though, we have two choices. either undo the bias in the x direction or do the same bias in the y direction. This second option is what Mercator does. So before delta b becomes delta y, we have to multiply it by secant b. This means the Mercator projection can be defined by delta x equals delta a and delta y equals secant b times delta b. But wait a minute, map projections aren't defined with delta x and delta y. They're defined with x and y. These describe how fast those variables change, but what about the actual values of those variables? Well, this is where calculus comes in. We can turn the original equations into differential equations. We can then solve them by integrating. To do this, we have to rearrange and then replace delta with d. That's because delta is used for small but concrete changes, but calculus is concerned with infinitely small changes. Integrating dx dA equals 1, we get x equals a. Integrating dy dB equals secant b, we get y equals ln of secant b plus tangent b. Technically, there are constants here, but all they do is move the map around on the page. If you look closely at these equations, you might notice that as latitude approaches 90 degrees, y approaches infinity, and the same thing for negative 90 and negative infinity. For that reason, the Mercator projection doesn't actually show the whole Earth, because it would have to be infinitely tall. There have to be cutoff points. If you cut it off at b equals 85 and negative 85, you get a map that looks like this. Now you might be thinking, why spend all that work for an ugly map that doesn't even show the whole Earth? Well, although it does have many disadvantages, there's one thing it does better than any other map. This is that it's 100% conformal. Local shapes and angles are always preserved. Not only is this great for zooming in, but it's also excellent for navigation. If you set sail at a constant bearing or direction on a compass, you can use straight lines on the Mercator projection to know exactly where you land. And in this aspect, no other projection can even compare. In fact, Gerardus Mercator himself first published the map in 1569 as a new and augmented description of Earth corrected for the use of sailors. But wait a minute, in 1569, calculus wasn't even invented yet. So how did he come up with it? Well, he never explained how he made it, but it was probably using data from rhumb lines, aka loxodromes, aka lines of constant bearing. The conformal property comes at a cost, though. The Mercator projection distorts the size of things more than any other map. The classic example is that Greenland looks comparable in size to Africa, when in reality it's smaller than even just the DR Congo. People like to hate on the Mercator projection because of its area distortion, but something to consider is that it was made with a very specific goal in mind, and it achieved that goal perfectly and better than any other projection. It's not designed for general use maps. As for why it's used so often in contexts where it doesn't fit, that's a different story, but don't hate the map itself. For doing one thing really well and doing other things not so well, its total score is 11. A similar projection is the Gauss stereographic. It's a Mercator-like projection, but it can actually show the whole Earth, and there's less area distortion. A consequence of this, though, is that it loses the conformal property, so it gets a score of 12. For this next projection, we have to rewind a bit. Earlier in the video, I said that going from actual distance to longitude and latitude, there's a bias in the x direction, and the two options to fix it are undoing it in the x direction or doing the same bias in the y direction. The second option is what Mercator does, but what about the first option? Well, to do that, we need to cancel out secant b, which can be done by multiplying by cosine b. This results in the equations delta x equals delta a times cosine b, and delta y equals delta b. Using the same process as before, we can make differential equations. After this, it's really easy to integrate, and we get x equals a times cosine b, and y equals b. This results in the sinusoidal projection. It may not be the prettiest, but it has some really cool properties. Firstly, it keeps horizontal lines to scale no matter where they are on the map. This is a property that none of the other projections have. Secondly, it preserves the area perfectly. For any two regions, if they have the same area on the map, then it means they have the same surface area on the globe. The unfortunate downside of all of this is that orientation and shape are both way off. For example, in reality, Australia looks like this, but on the sinusoidal projection, it looks like this. Regions near the middle of the map look fine, but as you go further out, they become more and more skewed. So is there any way to modify it and fix the skew while still maintaining the equal area property? Well, kind of. Using a technique called interrupting the map, you can create several small and disconnected pieces. Some slight modification results in this, the good homolocine projection. It keeps the continents natural looking and cuts them apart at the oceans. But it's actually not that simple. It uses the sinusoidal projection for latitudes less than 40, but for the rest, it uses another projection called the mole-wide elliptical, which I will cover later in the video. As a result, you can clearly see corners where it changes projection types. This even applies to landmasses. Just look at the Iberian Peninsula. For those reasons, its score is not very high, but it is still equal area. For this next type of projection, we need to go back to the idea of projecting onto a cylinder. The last time, that projection didn't turn out the best, but there's actually another way to do it. Instead of projecting light from a central point, we can project it from a central line that passes through the poles. This means every ray of light is parallel to the equator. It also means the cylinder doesn't have to be infinitely tall to include the whole Earth. In fact, its height is actually the same as Earth's diameter. When you unwrap it, you can also see that the length of the map is the same as the circumference of Earth. Circumference is pi times diameter, so this results in a very long rectangle with an aspect ratio of 1 by pi. This is known as the Lambert cylindrical equal area projection. It's defined by x equals a and y equals sine of b. As you can see, shapes near the poles are extremely distorted, while those near the equator are almost unchanged. Believe it or not, this distortion actually gives it the equal area property. That's because when you take an area from the sphere and project it onto the cylinder, it becomes wider in the x direction, but shorter in the y direction. As it happens, these two opposite forces cancel each other out perfectly. In fact, there's a lovely video about this exact phenomenon, which I highly recommend. Going back to the map though, it has some clear issues. Distances are distorted in both the x and y directions, and shapes become nearly unrecognizable. Changing the aspect ratio can help though. It makes some areas better, but some areas worse. Adjusting just a little bit results in the Bearman projection. Adjusting some more produces the Hobo-Dyer. Adjusting a lot produces the Gall-Peters projection. Unfortunately, they all still have the same issues, so their scores aren't much different. All of the output maps so far have been represented in 2 dimensions using rectangular coordinates, but another option is polar coordinates. Instead of using 2 distances, they represent points with 1 distance and 1 angle. These are called r and theta respectively. Since this system still has 2 inputs and 2 outputs, we can just use them directly. So theta equals a and r equals b. That results in the Azimuthal Equidistant projection. Something interesting about this projection is that it's taken literally by flat earthers, and they think the Earth is actually shaped like this. It's also used on the United Nations emblem. Unfortunately, it has many of the same issues as previous maps, and polar coordinates just aren't that useful for projection. So far, we've looked at direct results from several methods, but the most popular map style is actually the compromise style. This is when you take an existing type, usually the equirectangular, and make minor adjustments, usually emphasizing aesthetics. You can then end up with a well-balanced map. There are so many potential adjustments you can make, so I can't possibly cover every compromise map, but I will try to cover the most important ones. The Robinson projection shortens length based on a table of values to create a nicely balanced map. In my experience, this is the most widely used compromise projection. The mole-wide projection is designed so that every meridian is an ellipse. Interestingly, this actually means it has the equal area property. The times projection is a rounded version of the Gauss stereographic. Van der Grinten is Mercator-like, but it makes the map circular. Its formulation is very complicated. The Kavraisky 7 and Wagner 6 are basically the same thing, but with different aspect ratios. The Wagner 6 came first, but I think the Kavraisky 7 looks slightly better. The Eckert 2 turns the world into a hexagon, while being equal area. The Eckert 4 is also equal area, but it has more of a rounded look. The Winkel triple goes for a well-balanced approach, and has a complicated formulation method. Natural Earth is another Robinson-like projection, but it's defined by polynomial functions. And then finally, Equal Earth is Robinson-like, but it has the equal area property. Its formulation looks complicated, but apparently it's really simple for computers. This projection actually has a really interesting origin story. In 2017, Boston public schools were tired of the area distortion of the Mercator projection, so they wanted to switch to an equal area map. This is definitely a good idea, but instead of going for a compromise equal area map like the Eckert 4, they went for the Gauss-Peters. As a response, the Equal Earth projection was made to show them that it's possible to be equal area without ridiculous shape distortion. This projection has to be one of my favorites, because it has a really beautiful compromise aesthetic while still having the equal area property with relatively little distortion. You see, there are three main types of distortion. These are shape, size, and direction. Every projection will have some degree of distortion, but it will be distributed differently between these three categories. Mercator minimizes shape and direction distortion at the cost of size distortion. Dymaxion minimizes shape and size distortion at the cost of direction. The third extreme is the Lambert projection, which minimizes size and direction distortion, but has some of the worst shape distortion possible. These three maps all have their own unique advantages, but for general use maps, they're not that good. That's because the purpose of general use maps is to help people understand what the Earth really looks like. For that reason, the best approach is to distribute the distortion evenly across these three categories. A great example is the Winkel triple. In fact, the triple in its name literally refers to this exact goal. It's no wonder why this map is the standard for National Geographic. When the Boston public schools changed from Mercator to Gauss-Peters, though, all they did was go from one extreme to another. Apparently, they did it because they thought the Mercator was Eurocentric. Of course, the Mercator projection wasn't designed to be Eurocentric, and luckily most people know that, but Europe is still enlarged due to its latitude. For that reason, it's perfectly reasonable to want to fix this with a different projection. The issue, though, is that they went with the worst possible option. For an equal area map, they could have gone with Bearman, Mole-wide, Good Homolocine, Dymaxion, or Eckert 4. Instead, they went with the Gauss-Peters, which is arguably more Eurocentric than the Mercator. You see, with the Bearman projection, most of the world looks fine at the expense of Northern Europe being stretched. The Gauss-Peters, on the other hand, makes Europe look fine at the expense of the rest of the world being stretched. Sure, the map may be equal area, but Europe is just about the only place that's shown accurately. Throughout this video, I've been comparing regions on distorted maps to how they actually look. But how is this possible? Do I have some kind of perfect map projection that shows everything accurately? Well, kind of. There's actually one final type of projection that I haven't talked about yet. This is the perspective method. A perspective projection is what you would actually see if you looked at Earth from a distance. It can also be thought of as taking a picture of Earth from some far-off location. You can do this at any location depending on what you want in the map. Areas close to the center of the picture look pretty accurate, but further areas look more distorted. Eventually, the Earth's surface curves so much that it goes back behind itself and you can't see anymore. For this reason, you can never show more than half of the Earth. In fact, when the camera's really close, the amount you see is a lot less than half. As you move the camera further away, the proportion of Earth you see increases. It approaches 1/2, but never equals 1/2. To do that, you would need it to be infinitely far away. It's still possible to compute what it would look like, though, using the orthographic projection. It takes points on the globe and projects them onto a flat surface in such a way that it keeps all rays of light parallel to each other. It ends up looking not much different than the finite distance perspectives, and that's because it's actually the limiting case as distance increases. The thing about these perspective methods is that they can't show the whole Earth. For that reason, they're probably one of the best ways to show a single region, but one of the worst ways to show the whole Earth. As you can see, each map projection has its own purpose. Some are made with specific applications in mind and only focus on one category. Others go for a more balanced approach. Unfortunately, though, a perfect projection does not exist. At the end of the day, the most accurate way to view the Earth is a globe. It doesn't have any distortion, but it's not really a fair competition. It may be more accurate, but projections are better in one crucial way: accessibility. They can be put in books, and this makes geography knowledge widely available. For that reason, the importance of map projections cannot be understated. They're one of the most fundamental tools to understand the world, like the geography equivalent of writing itself. That's why I find them so interesting. We see them so often, but most people take them for granted. So the next time you see a map, maybe take a moment to figure out what projection it uses and remember all the math that goes into it. And that's the end of the video. Thank you for watching all the way through. This is only my second video, so I really do appreciate any and all feedback. Don't forget to like and subscribe, but most importantly, comment ideas for videos I should make in the future. This helps me more than you can imagine, because it gives me motivation and something to work towards. So thank you again for watching, and I'll see you in the next video.